Any questions? Okay. Let's see, what's it over here? I'm going to say I'm done with chapter 3, so master sets do everything. Let's talk about, in chapter 2, we were talking about forces. In chapter 3, we talked about describing motion. So chapter 4 is combining the two. This is known as Newton's second law, which I'll abbreviate N2L. Newton's second law of motion. He's got 3 major laws of motion. And the first one is just pretty much this. When I talked about equilibrium, if in essence equilibrium means the acceleration is 0, and I know that acceleration is the change in velocity over the change in time. Therefore, if the acceleration is 0, the change in velocity has to be 0. So this means that the change in velocity is 0. And based upon Newton's second law, if acceleration is 0, the total force must be 0. Now, typically it's just written as F equals ma. That F is indeed the total force. We're not saying there are no forces involved, we're just saying that they add up to 0. So this is the total force. And as I wrote in one of the videos, it can also be written as F net or F total, or just put the sigma in front of F. The sigma, just when you ever see that, that means sum. The progression is, I want to indicate something about a sum. Sum starts with an S. Sigma starts with an S. Sigma. And it's a capital sigma. So it's just shorthand notation, means adding them all up. If acceleration is not 0, in other words, we are not dealing with equilibrium, then there's got to be a net force acting on it. Thus, when we were doing the complex force diagram over here, that I indicated the direction of acceleration, so you would know at least there's got to be some force in that direction. So let's start with a simple example with numbers. So I have a 5 kilogram box here. I'm pushing on it with a 3 Newton force. What is the acceleration? Well, first off, 5 kilograms. What is that? Not looking for a translation to something else. What if I say 5 kilograms? What does that?
Mass.
Yes. So that's the M. The total force? We can be more specific than that.
3 newtons to the left.
Which way?
3
To the
newtons
right.
to the right.
Yeah, okay. Yes, 3 newtons to the right, and just as a shorthand, so I don't have to write all that out, I'll just put a plus sign with an arrow pointing that way, and that will tell me that to the right is just a positive thing. So now we can plug and chug. F equals ma. I've got 3 newtons is equal to 5 kilograms times the acceleration. Now the plus sign in front is just to re-emphasize the fact that we are dealing with a vector here, but it's optional. So how do you solve it? So the math problem is right there, 3 divided by 5. And if you're a fan of fractions, 3/5 is your answer. Or for you decimal fans out there. So I got 0.6 is equal to A, because the 5 cancels out, the kilograms cancels out. What are the units here?
Meters per second.
There we go, as a group we got it, meters per second squared. But I got newtons divided by kilograms. Could I write newtons per kilogram? Is 0.6 newtons per kilogram a valid answer? Why not? Units? Is everyone good with Chrislin's answer?
There's no time in newtons and kilograms.
What is a newton?
It's a weight, right?
Oh, or general force. It's a unit of force. Yeah, it turns out that a newton, so it shows up a little bit better. I've done the 3 lines before, haven't I? Okay, I got nods from a couple people. All right, so newton is defined as a kilogram times meter per second squared. So if you do a newton divided by kilograms, kilograms would divide out and you're left with meters per second squared. This actually is legitimate. It's not traditional. If you wrote 0.6 newtons per kilogram, if I did that on a problem, they'd take a moment and go, wait a second, that's odd. Meters per second squared is what I would expect, but newtons per kilogram is acceptable. And so that's the basic Newton's second law problem. If, let's see, let's take this and then add 4 newtons pushing to the left. First off, we're plugging in. The question is, what is the acceleration? So I'll look at this. And, well, I know the mass, it's given. What's the total force?
-1.
Yeah, I got 3 to the right, I got 4 to the left, the net is 1 to the left. Or you, if you like doing the math, 3 plus -4, -1. So I have -1 Newton is equal to 5 kilograms times the acceleration.
Meters per second squared.
Yeah. Questions up to here? Let's combine stuff. Let's combine this with the stuff that we've done in the past. Let's see, there's the marker.
Is sauce in the room?
I believe she's in 306.
Wait, the lab?
The lab.
Alright,
Yes.
so just check if she was out there.
Oh,
Do you have a cup of papers?
yes.
Sitting right. Just trying to get it through.
And now the world will see. So, a 6 Newton force pushes north on a kilogram box. Which is on a frictionless surface. If the force is constant. All that is the 6 Newton. Oops. Is the box going after 4 seconds? And how far has it traveled? Let's see, pushes north, let's see. I do need to throw in one other thing initially. At rest. All right, this should combine various chapters together. All right, so let's figure out the bits and pieces. We've got 3 numbers explicitly in there. First off, the 6 newtons. What is that telling us?
Force.
All right, so I know that the force is 6 newtons. However, it's a vector, so we do need to throw in one other bit.
North.
And why don't we just go, north is positive. It's a one-dimensional problem. So it's positive. All right, so the next thing we have is 8 kilograms.
That's our mass.
Okay, so mass equals 8 kilograms. And 4 seconds.
Time.
Now, I know Newton's second law. I know that F equals ma. Well, I know 2 of those things, so I can find the third one. I'm trying to find my final velocity and my displacement. So the way I worded it, how far has it traveled? Actually, I'm trying to find distance, but it only travels in one direction, so it's the magnitude of my displacement. So I guess technically I'm trying to find delta x. All right, so let's just start out with what we can do. Oh, I do know one other piece of information.
Frictionless surface.
What does that tell us?
It keeps accelerating. It keeps accelerating.
Okay. Even with friction, it might keep accelerating.
There's like no frictional force to account for in the problem.
Okay. Yeah, so that 6 Newton force, that's an example of other. And we don't know what's causing it, but the lack of frictional forces means that there's not an additional force that we have to worry about. And, oh no, one other piece of information.
That the force is constant?
Say it again?
That the force is constant?
That's sort of, it is constant, and that's necessary. I feel like it's implied in F equals 6 newtons where I didn't put it in I didn't graph anything and I didn't add more detail to that. But yes, that is important.
Is it initially at rest?
Yes, and that's the other piece. What does that tell us?
Starting at 0.
Initial velocity, 0 meters per second. All right, so first let's plug into here. So if this were a test question, I would have broken it down. I would start out with, what is the acceleration? Like a jug. So 6 is equal to 8a. That's the math problem.
A equals 0.75.
Divide both sides by 8, you get a all by itself. Units.
Meters per second squared.
All right. So we have the acceleration. It would have to be in the same direction as the force. So it's in the positive direction. I know 3 things. I know time, initial velocity, acceleration, so I should be able to figure those out. And we can set this up several different ways, but if I did time in seconds and velocity in meters per second, I know when time is 0, 1, 2, 3, and 4. That is 0. After 1 second, what is the velocity?
175.
2 seconds?
1.5.
3 seconds?
2.25.
And 4 seconds?
3.
So, what is the final velocity?
3 meters. Meters per second.
Okay. What's the final speed?
4. Oh, never mind.
Final velocity is 3 meters per second north. What's the final speed? I'm willing to bet you're overthinking it.
Is it velocity?
Sorry?
Actually,
What is velocity for speed? What's the difference between velocity and speed?
Velocity is the direction, the speed is just the magnitude without direction.
Okay, say velocity again?
Velocity is it's the speed and direction of which
Okay.
an object is going.
What I heard before was that it was just the direction. So.
Yeah, well, yeah.
Okay, so it's the speed and the direction. So if my final velocity is 3 meters per second north, what's my final speed?
3 meters per second.
Yeah, it's just 3 meters per second. So final speed, 3 meters per second. All right. So I've gone from 0 to 3 meters per second in 4 seconds. Roughly 7 miles an hour. I'm trying to figure out displacement. So what's my average velocity?
1.5 meters per second.
So on average, I'm going 1.5 meters per second for 4 seconds. What's what's my displacement? Or how would you find it?
6 meters.
Say it again?
6 meters. 6 meters.
Yeah. How'd you get it?
1.5 meters per second times 4 seconds.
Yep. So that's 6 meters north. And was the distance traveled?
6 meters. 6 meters.
Say it again?
6 meters.
Yep. And done. That's the end of that problem. Questions before I add other dimensions? All right, I'm going to go grab, let's see, I want pulley, cart, string, and the masses already, and masses. Pulley, cart, string, and masses. Go ahead and pause this. All right, so I know that this card is roughly a half a kilogram, and hanging on here, I've got 50 grams. So let's make a prediction about what the acceleration is.
50 grams would be like 0.05 kg.
Pardon?
Would 50 grams be 0.05 kilograms?
Yes, it would. All right, so the basic setup here is I've got cart attached to a string. I have a pulley here. It's a super pulley. So we will assume that it is frictionless. So I have cart, MC for cart, MH for hanging mass. Mass of cart is approximately 0.5 kilograms and hanging mass 0.05 kilograms. And that is taken. All right, so let's do a force diagram. First off, let's do a force diagram